Right now, somewhere in the distant universe, a cloud of gas the size of a star is falling towards something it cannot escape. As it spirals inward, friction heats it to millions of degrees. The gas begins to glow, not faintly, but with the light of 1 trillion suns. All of that energy is pouring out of a region smaller than our solar system. This is a quasar, the brightest sustained object in the known universe. And what most people don't realize is that this blinding light isn't coming from the black hole itself. Black holes emit nothing. The light comes from the violent, chaotic engine surrounding it, a machine built from superheated gas, tangled magnetic fields, and forces so extreme they turn ordinary matter into the most luminous thing in existence. Tonight, we're going inside that engine to see exactly how it works. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Imagine taking every star in an entire galaxy, hundreds of billions of them, each one a roaring nuclear furnace converting millions of tons of hydrogen into helium every single second, and combining all of their light into a single point. That is roughly what a quasar produces. A single quasar can outshine 1 trillion stars, not 1 billion. 1 trillion. That is a 1 followed by 12 zeros, each digit representing a sun's worth of luminosity stacked on top of the last. And all of that light, all of that energy, pours out of a region so compact that it would fit comfortably inside our solar system. This is not an exaggeration. It is measured fact. When astronomers first calculate quasar luminosities in the early 1960s, they did not believe their own numbers. The figures seemed physically impossible. Nothing they knew of could produce that much energy from that small a space. And for good reason. If you try to explain quasar luminosity using any familiar energy source, the math falls apart almost immediately. Let us start with the most basic energy source humans know: chemical energy. When you burn wood or gasoline, you are breaking and rearranging molecular bonds. This releases energy, but not very much per unit of mass. If you burned a mass equal to our entire sun as chemical fuel, you could sustain quasar brightness for only a few thousand years. Quasars shine for millions of years. Chemical energy cannot explain them. What about nuclear energy? Nuclear fusion is what powers every star in the universe. In the core of our sun, hydrogen nuclei slam together at temperatures exceeding 15 million degrees and pressures 260 billion times Earth's atmospheric pressure at sea level. These collisions fuse hydrogen into helium, releasing energy according to Einstein's famous relationship between energy and mass, E equals mc squared. Fusion is enormously more efficient than chemical burning. The sun converts roughly 600 million tons of hydrogen into helium every single second, and it has been doing this for 4.5 billion years. But here is the critical detail that most people overlook. Nuclear fusion converts less than 1% of the fuel's rest mass energy into radiation. For every kilogram of hydrogen fused, only about 7 grams worth of mass actually becomes energy. The other 993 grams remain as matter. Fusion is powerful by everyday standards. It lights every star you see in the night sky, but it is surprisingly inefficient by the standards of physics. Even if you could fuse an entire sun's worth of hydrogen with perfect efficiency, Extracting every last fraction of energy that fusion allows, you could not sustain quasar-level luminosity for more than a small fraction of the time these objects are observed to shine. So chemical energy fails by an enormous margin. Nuclear fusion fails too, not by quite as much, but still decisively. What is left? What possible mechanism could convert enough mass into enough energy to explain the most luminous sustained objects in the known universe? The answer is gravity, specifically gravitational potential energy released through a process called accretion, the spiraling infall of matter toward an extraordinarily massive, compact object. And the object at the center of every quasar is a supermassive black hole. Not a star, not a cluster of stars. A single black hole with a mass ranging from millions to billions of times the mass of our sun, compressed into a region of space-time so warped that nothing, not even light, can escape once it crosses the boundary known as the event horizon. Here is what makes accretion so remarkable. When matter falls toward a black hole, it accelerates. It picks up kinetic energy, the energy of motion, converted directly from gravitational potential energy, the energy stored in its position above the gravitational well. The deeper the gravitational well, the more energy is released during the fall. And supermassive black holes create the deepest gravitational wells in the known universe. The closer the infalling matter gets before it finally crosses the point of no return, the more of its gravitational potential energy has been converted into heat and light and motion. Under the right conditions, accretion onto a rapidly spinning black hole can convert up to roughly 40% of the infalling matter's rest mass energy into radiation. Compare that to fusion's fraction of a percent. Accretion is not just more efficient than fusion, it is roughly 50 to 60 times more efficient. Kilogram for kilogram, nothing in the universe extracts more energy from matter than the process of falling into a black hole. This is what makes accretion the most efficient sustained energy source in existence. And this is what powers a quasar, not the black hole itself. Black holes do not emit light. They do not glow. They do not radiate. In isolation, a supermassive black hole is utterly dark, invisible against the blackness of space. What powers a quasar is the matter spiraling into the black hole, heated and compressed to extreme conditions during the long fall inward. The black hole provides the gravitational pit. The infalling gas provides the fuel, and the process of falling, spiraling, compressing, and heating provides the energy. The black hole is the stage. Accretion is the performance, but matter does not fall straight in. This is a critical point that changes everything about how the engine works. If you drop a ball on Earth, it falls straight down because the only force acting on it is gravity pulling it directly toward the center of the planet. There is no significant sideways motion. But in space, gas almost never approaches a black hole on a perfectly straight trajectory. Nearly always, the gas has some sideways motion, some angular momentum inherited from the galaxy around it, from the orbits of stars and clouds in the surrounding environment, from the turbulence and rotation of the gas itself. Angular momentum is a measure of rotational motion, and it is conserved. It cannot simply disappear. And it changes everything about how gas reaches the black hole. Think about what happens when a figure skater pulls their arms in during a spin. They spin faster because angular momentum is conserved. It concentrates rather than disappearing. The same principle governs gas falling toward a black hole. As the gas moves closer to the center, its orbital speed increases. The closer it gets, the faster it orbits, and the increasingly rapid orbital motion creates a centrifugal effect that resists further infall. The gas cannot simply plunge straight in. It has too much sideways momentum. It would overshoot, swing around, and fly back out the other side. Unless something removes that angular momentum gradually, letting the gas drift inward slowly rather than falling freely. This is where the accretion disk forms. The gas settles into a flattened, rotating disk around the black hole, a vast swirling structure that can stretch across billions of kilometers. The disk forms because rotation naturally flattens things. Any gas moving on tilted or inclined orbits inevitably collides with other gas on different tilted orbits. These collisions cancel out vertical motion, the up and down component, while preserving the overall rotation. Over time, all the gas settles into a single plane of average rotation, creating a thin, spinning disk. Picture a pizza chef tossing dough. The spinning motion flattens the dough into a disk. Gravity and angular momentum do the same thing to gas around a black hole, just on an incomparably larger scale. Inside this disk, something remarkable happens. Different layers of the disk orbit at different speeds. Gas closer to the black hole orbits faster than gas farther out. This is not a choice. It is a mathematical consequence of gravity. Kepler's laws of orbital motion demand it. In any gravitational field, objects closer to the center must orbit faster to avoid falling in. The inner edge of a quasar accretion disk might be orbiting at a significant fraction of the speed of light, while the outer edge moves comparatively slowly. This difference in speed between adjacent rings of gas is called differential rotation. And differential rotation is what makes the entire engine work. Imagine two cars on a circular racetrack. One is in the inner lane, going much faster. The other is in the outer lane, going slower. If you connected them with a rope, the rope would stretch and pull. The faster inner car would tug the outer car forward, trying to speed it up, and the outer car would drag the inner car backward, trying to slow it down. Now, imagine this happening not between two cars, but between every adjacent ring of gas in a disk that contains millions of solar masses of material. Each ring tugs on its neighbors. Faster inner gas pulls on slower outer gas, and slower outer gas pulls back on faster inner gas. This interaction between adjacent layers moving at different speeds creates friction. Friction in the disk is the actual power source of a quasar. Not the black hole's gravity directly, but friction within the spiraling gas converting orbital energy into heat and light. And this friction does two things simultaneously. First, it converts orbital kinetic energy into thermal energy. The gas heats up enormously as friction dissipates the energy of its motion. Second, and just as importantly, friction transfers angular momentum outward through the disk. When inner gas loses angular momentum to outer gas, it can no longer maintain its orbit at that distance. It drifts inward, closer to the black hole, deeper into the gravitational well. This releases more gravitational potential energy, which heats the gas further, creating more friction, which transfers more angular momentum outward, which allows more gas to drift inward. It is a self-sustaining cycle, a feedback loop that keeps the disk churning. Gas spirals slowly inward through the disk, getting hotter and denser and faster as it descends, radiating the energy of its gravitational collapse as light. But here is a problem that puzzled astrophysicists for decades. Ordinary molecular viscosity, the kind of friction you feel when you stir thick honey or drag your hand through water, is far too weak to explain the angular momentum transport needed in an accretion disk. If the only friction operating were ordinary gas viscosity, the disk would take longer than the current age of the universe to funnel gas inward at the rates needed to produce observed quasar luminosities. The numbers did not work. Something else had to be generating enormous turbulence within the disk, churning it violently, creating an effective friction millions of times stronger than molecular viscosity alone. For years, theorists simply assumed this turbulence existed and gave it a name, but they could not explain what caused it. The answer came in 1991, when astrophysicists Stephen Balbus and John Hawley demonstrated that a weak magnetic field threading through a differentially rotating disk triggers a powerful instability. This is the magneto-rotational instability, and it is one of the most important discoveries in the history of accretion physics. Here is how it works. Imagine two small parcels of gas sitting in the disk, one slightly closer to the black hole than the other, connected by a magnetic field line that acts like a weak, elastic spring. The inner parcel orbits faster than the outer parcel because of differential rotation. As the inner parcel pulls ahead, the magnetic spring stretches between them. The spring pulls backward on the faster inner parcel, slowing it down slightly. At the same time, the spring pulls forward on the slower outer parcel, speeding it up slightly. Now here is the crucial twist. What happens when you slow down a piece of gas that is already in orbit? It loses energy and drops to a lower orbit, closer to the black hole. What happens when you speed up a piece of gas in orbit? It gains energy and moves to a higher orbit, farther from the black hole. So the two parcels actually move apart. The inner one falls inward, the outer one drifts outward. The magnetic spring stretches even more. The force between them grows stronger, which pulls the inner parcel even more inward, and the outer parcel even more outward. The effect amplifies itself. It is a runaway process. A tiny initial disturbance grows exponentially until the entire disk is seething with turbulence. This turbulence, driven by the magneto-rotational instability, generates chaotic motion throughout the disk. Magnetic field lines tangle, stretch, snap, and reconnect in wild, unpredictable patterns. The resulting turbulence acts as a powerful, effective viscosity, far stronger than any molecular process could produce. This turbulent viscosity is what drives angular momentum transport in the disk and allows gas to spiral inward at the rates needed to power a quasar. The magneto-rotational instability solved a mystery that had haunted accretion physics since the 1970s. It showed that any weakly magnetized, differentially rotating disk is inherently unstable. Turbulence is not just possible, it is inevitable. Angular momentum transport is automatic. The disk churns itself, and in doing so, it lights up the universe. Now let us talk about how efficient this process really is, because the numbers are staggering. In any gravitational field, the energy released by an object falling from a great distance down to some radius depends on how deep the gravitational well is at that radius. The deeper the well, the more energy is released. For a black hole, matter can orbit extremely close to the event horizon before making its final plunge. This means the total gravitational potential energy released before the gas crosses the point of no return is enormous. For a black hole that is not spinning, there exists a critical boundary called the innermost stable circular orbit. This is the closest distance at which matter can maintain a stable circular orbit around the black hole without spiraling inward uncontrollably. Below this boundary, no stable orbits exist. Any matter that crosses this threshold falls rapidly inward and plunges through the event horizon. For a non-spinning black hole, the innermost stable circular orbit sits at 3 times the Schwarzschild radius, which itself defines the size of the event horizon. By the time gas has spiraled down to this boundary, it has already converted roughly 6% of its rest mass energy into radiation. 6% may not sound impressive at first, but remember that nuclear fusion in the cores of stars manages less than 1%. Accretion onto even a non-spinning black hole is already 6 times more efficient than the process that powers every star in the sky. But here is where it gets truly extraordinary. Real black holes spin. They rotate, often very rapidly, because the gas falling into them carries angular momentum that gets added to the black hole's own rotation over millions of years of feeding. And spin changes everything. A spinning black hole drags the surrounding space-time around with it, an effect called frame dragging predicted by Einstein's general theory of relativity. This frame dragging allows matter to orbit closer to the event horizon than would be possible around a non-spinning black hole. For a black hole spinning it close to its theoretical maximum rate, the innermost stable circular orbit shrinks dramatically. It can move all the way down to near the event horizon itself. The gas spirals closer and closer, releasing more and more gravitational potential energy with every inward step. The conversion efficiency in this case can reach roughly 42% of the infalling matter's rest mass energy. 42%. Nearly half of everything that falls in gets converted into energy before it crosses the event horizon and vanishes forever. To put this in perspective, if you could convert a single kilogram of matter into energy at 42% efficiency, you would release roughly 3.8 times 10 to the 16th joules. That is approximately the energy output of a large nuclear power plant, operating continuously for an entire year. From 1 kilogram of gas falling into a spinning black hole, 1 kilogram. This is why accretion onto supermassive black holes produces quasar luminosities without requiring impossibly large amounts of fuel. You do not need to devour entire galaxies of matter. You just need a steady supply of gas falling into an extraordinarily deep gravitational well, with friction converting orbital energy into heat along the way. A quasar consuming roughly 1 to a few solar masses of gas per year, just 1 to a few times the mass of our sun annually, can outshine an entire galaxy containing hundreds of billions of stars. The gravitational engine is that efficient. The temperature of the accretion disk varies enormously from its outer edge to its inner rim. At the outer regions, far from the black hole where the gas orbits relatively slowly and friction is mild, temperatures might reach a few thousand degrees. This is comparable to the surface temperature of a cool red star. Gas at these temperatures glows in infrared and reddish visible light, producing a warm glow at the disk's periphery. Moving inward through the disk, temperatures climb steadily. The gas orbits faster. The differential rotation between adjacent rings is more extreme. Friction is more intense. Gravitational potential energy is being released at a greater rate. In the middle regions of the disk, temperatures reach tens of thousands of degrees, comparable to the surfaces of the hottest blue stars. The gas here glows in visible and ultraviolet light, contributing a brilliant blue-white radiance. At the innermost regions, closest to the black hole and the innermost stable circular orbit, temperatures soar into the hundreds of thousands of degrees. This is far hotter than the surface of any star. The gas emits predominantly in the ultraviolet and extreme ultraviolet, flooding the surrounding environment with radiation that will be invisible to human eyes but carries tremendous energy. For the supermassive black holes powering the most luminous quasars, the peak thermal emission from the disk falls squarely in the ultraviolet. This is why quasars appear so strikingly blue when observed through telescopes. Their light is dominated by the hot inner disk, and the inner disk is hottest in the ultraviolet. There is a distinctive feature in quasar spectra that astronomers call the big blue bump, a broad excess of ultraviolet and optical emission that corresponds directly to thermal radiation from the accretion disk. When astronomers observe this feature, they know they are seeing the disk itself, glowing white-hot with the accumulated heat of friction and gravitational compression. But the disk is not a single temperature object like a star, where you can assign one number and call it the surface temperature. The accretion disk is a multi-temperature structure. Each concentric ring sits at a different distance from the black hole, experiences a different orbital speed, a different degree of friction, a different intensity of gravitational energy release, and therefore glows at a different characteristic temperature and wavelength. The cool outer rings contribute infrared radiation. The warm middle rings contribute visible and ultraviolet light. The blazing inner rings contribute extreme ultraviolet emission. Layer all these rings together, and you get a broad, smooth spectrum stretching across a huge range of the electromagnetic spectrum, from infrared, through optical, through ultraviolet. This multi-temperature thermal signature is distinctive. Almost nothing else in the universe produces exactly this kind of broad, blended emission. When astronomers detect it in the light from a distant object, they know with confidence that they are looking at an accretion disk spiraling around a supermassive black hole, and at the very inner edge of the disk, something final and irreversible happens. The gas reaches the innermost stable circular orbit, and there are no more stable orbits available. The gas cannot spiral any further through friction and angular momentum transfer. It cannot slow down gracefully and settle into a tighter circle. Instead, it plunges. It falls rapidly inward in a swift, final descent, crossing the event horizon in moments. Once past that boundary, the gas and all the energy it still carries are gone. Swallowed by the black hole, nothing returns, no light, no signal, no information of any kind. The event horizon is an absolute boundary, and everything that crosses it is lost to the outside universe forever. But here is the remarkable thing. By the time the gas reaches that final plunge, it has already given up an enormous fraction of its energy to the universe. The disk extracted that energy through friction, through compression, through the slow, grinding, relentless process of spiraling inward over thousands or millions of individual orbits. The radiation has already escaped. It has already been emitted, already traveled outward through space at the speed of light, already carried the story of accretion to telescopes billions of light years away. The black hole gets the matter. The universe gets the light. This is the fundamental bargain at the heart of every quasar. Matter falls in, energy comes out, and the amount of energy that comes out, relative to the amount of matter that falls in, makes accretion the most powerful, sustained energy process the universe has ever produced. What you are seeing when you observe a quasar shining from the distant cosmos is not the black hole. You cannot see the black hole. What you are seeing is the accretion disk itself. A swirling, superheated maelstrom of gas spiraling inward, glowing with the converted energy of gravitational collapse, radiating more light than a trillion suns from a region you could fit inside the distance between our sun and the nearest neighboring star. Every photon in that flood of light was paid for by a tiny parcel of gas surrendering its gravitational potential energy as it fell one step deeper into the well. Every wave of ultraviolet radiation, every pulse of infrared warmth, every ripple in the spectrum tells the same story. Matter converting the energy of position into the energy of light, gravity made visible, and this is still only the beginning. Because the accretion disk does not operate in isolation. Above it and below it, something even more violent is happening. Magnetic fields anchored in the turbulent disk are twisting and snapping, heating plasma to temperatures 1,000 times hotter than the disk itself, and launching structures so powerful they can reshape entire galaxies from the inside out. The disk is the engine, but the engine has components we have not yet seen. The accretion disk explains much of what makes a quasar so luminous. Its multi-temperature glow, from cool infrared at the outer edge to searing ultraviolet at the inner rim, accounts for a vast portion of the energy output. But the disk does not explain everything. When astronomers point X-ray telescopes at quasars, they detect an enormous flood of high-energy radiation that the disk alone simply cannot produce. The hottest parts of the disk reach temperatures of a few 100,000 degrees. That is more than enough to generate ultraviolet light. But X-rays require something much hotter. To produce the hard X-ray emission observed pouring out of quasars, you need temperatures in the hundreds of millions of degrees, possibly exceeding 1 billion. Nothing in the disk gets that hot. The energy is there, but the disk's surface temperature tops out well below what X-ray production demands. So where are these X-rays coming from? The answer lies in a mysterious region that astronomers call the corona. Not the solar corona you may have heard of during eclipse coverage, although the name was borrowed from the same basic idea. A quasar's corona is a diffuse cloud of extraordinarily hot plasma that hovers above and below the innermost regions of the accretion disk. Picture the disk as a flat, glowing surface. Now imagine a shimmering, nearly invisible haze floating just above that surface and just below it, sandwiching the inner disk between two layers of gas so hot that the temperatures defy everyday comprehension. The electrons in this coronal plasma are moving at a significant fraction of the speed of light. They carry so much kinetic energy that the effective temperature of the corona reaches hundreds of millions of degrees, and in some models climbs past 1 billion. This is far hotter than the center of any star, far hotter than any nuclear explosion, far hotter than anything you will encounter in the natural universe outside the most extreme environments near compact objects. But how does gas get this hot? The accretion disk itself is already extraordinarily energetic, yet it cannot produce coronal temperatures through friction alone. Something else must be pumping energy into this plasma, heating it far beyond what the disk's surface can achieve. And the answer, once again, involves magnetic fields. We already saw how the magnetorotational instability drives turbulence throughout the accretion disk, tangling and stretching magnetic field lines in the churning gas. Those field lines do not simply stay embedded quietly in the disk. In the turbulent inner regions, where orbital speeds approach a significant fraction of light speed, and the differential rotation between adjacent rings of gas is most extreme, magnetic field lines get amplified, twisted, and stretched to extraordinary tensions. Think of each field line as an elastic band embedded in the swirling gas. As the gas orbits and churns, these elastic bands get pulled tighter and tighter, storing more and more energy with every twist. Eventually, the tension becomes too great. Two oppositely directed field lines that have been pushed together by turbulence suddenly snap and reconfigure, releasing all their stored magnetic energy in a violent event called magnetic reconnection. Magnetic reconnection is one of the most powerful energy release mechanisms in astrophysics. When field lines snap and rearrange, the stored magnetic energy does not just disappear. It converts almost instantly into other forms. Some of the energy goes into heating the surrounding plasma to extreme temperatures. Some of it accelerates individual electrons and ions to enormous speeds, creating a population of ultra-fast particles. The result is a burst of thermal and kinetic energy concentrated in a small region above the disk surface. And this does not happen once. It happens continuously. All across the inner disk, field lines are constantly being wound up by turbulence, constantly being pushed together, constantly snapping and reconnecting. The corona is sustained not by a single event, but by a relentless barrage of reconnection events, each one dumping energy into the hot plasma above and below the disk. It is like a campfire fed by an endless supply of twigs. Each twig burns out quickly, but because new twigs are constantly being added, the fire never goes out. The corona persists as a permanent feature, maintained in its superheated state by the unending turbulence of the disk below. Now, here is where the corona produces X-rays. The mechanism is elegant and involves a direct interaction between the hot coronal electrons and the photons streaming upward from the disk. Remember, the inner disk is radiating enormous amounts of ultraviolet light. Those ultraviolet photons carry significant energy, but not enough to qualify as X-rays. As these photons rise from the disk surface and enter the corona, they encounter electrons moving at nearly the speed of light. When a photon collides with one of these ultra-fast electrons, something remarkable happens. The electron transfers some of its kinetic energy to the photon, boosting the photon's energy and frequency. A photon that entered the corona as an ultraviolet photon exits as an X-ray. This process is called inverse Compton scattering. In normal Compton scattering, a high-energy photon hits a slow-moving electron and loses energy to it. The photon gets redder and the electron speeds up. In inverse Compton scattering, the situation is reversed. The electron is moving faster than the photon, so energy flows the other way. The electron slows down slightly, and the photon gains energy, jumping up in frequency from ultraviolet to X-ray, or even higher. In a quasar's corona, this happens on an industrial scale. Trillions upon trillions of ultraviolet photons from the disk get scattered and boosted by the coronal electrons, producing the torrent of X-ray emission that astronomers observe. The spectrum of these X-rays carries a distinctive signature, a power law shape that tells astronomers exactly how hot and how energetic the coronal electrons are. By studying this X-ray spectrum, they can infer the corona's temperature, its density, and even its approximate geometry relative to the disk, all without ever seeing it directly. And that geometry is one of the most actively debated questions in quasar physics. We know the corona exists, we can measure its temperature and its X-ray output, but we are not entirely sure what shape it takes. Two competing models dominate the discussion. The first is called the sandwich model. In this picture, the corona is a broad, extended layer blanketing the inner disk from above and below, like two hot pancakes pressed against the disk's surface. The corona in this model is spread out over a large area, covering much or all of the inner disk. Reconnection events happen everywhere across this extended layer, and the resulting X-rays are produced over a wide region. The second model is called the lamppost model. In this picture, the corona is not spread out at all. Instead, it is concentrated into a compact source hovering above the black hole along its spin axis, like a single bright light bulb mounted on a pole directly above the center of the disk. In the lamppost model, the X-ray source is small, intense, and located very close to the black hole, perhaps only a few event horizon radii above the singularity. The X-rays radiate outward from this compact source in all directions, some traveling upward toward the observer, others traveling downward and striking the disk's surface below. The reason this distinction matters is that the geometry of the corona affects how we interpret the reflected spectral features that X-rays produce when they bounce off the disk. A compact lamppost source illuminates the innermost disk most intensely, producing strongly distorted reflection signatures shaped by the extreme gravity near the event horizon. A spread-out sandwich corona illuminates the disk more uniformly, producing less dramatically distorted features. Astronomers could reach different conclusions about the black hole's properties depending on which coronal geometry they assume. Getting the corona shape right is essential for reading the inner engine correctly. Recent observations from X-ray telescopes have provided evidence for both models, and the truth may be that neither is entirely correct on its own. Some quasars show X-ray behavior that matches the lamppost picture, with rapid correlated variability suggesting a compact source. Others show behavior more consistent with an extended corona. It is possible that the corona's geometry changes over time, collapsing into a compact configuration during some accretion states and spreading into an extended layer during others. The corona may be a dynamic, evolving structure rather than a fixed shape, constantly reconfigured by the same magnetic turbulence that creates it. The corona also interacts with the disk in another important way. Some of the X-rays produced in the corona travel downward, back toward the disk surface. When these high-energy photons hit the relatively cool disk material, they get absorbed and re-emitted, or they scatter off atoms in the disk, producing characteristic spectral features. The most famous of these features is the iron K-alpha emission line, produced when X-rays knock inner electrons out of iron atoms in the disk, and the atoms emit a specific wavelength of light as they recover. Because this iron emission comes from gas orbiting deep in the gravitational well of the black hole, the line gets distorted by extreme gravitational redshift and Doppler effects. The shape of this distorted iron line tells astronomers how close the emitting material is to the event horizon, and how fast the black hole is spinning. It is one of the most powerful diagnostic tools in black hole astrophysics, and it exists entirely because the corona bathes the inner disk in X-rays that the disk then processes and reflects back toward our telescopes. So the corona is an integral part of the quasar engine. It is created by the disk's own magnetic turbulence, sustained by continuous magnetic reconnection, and produces X-rays through inverse Compton scattering. Without the corona, quasars would be bright in ultraviolet light, but nearly invisible in X-rays. The corona transforms the disk's thermal radiation into a much harder, more penetrating form of light, adding another layer to the quasar's already extraordinary output. But magnetic fields near the black hole do something even more spectacular than building a corona. Under the right conditions, they create the most dramatic structures in the entire universe. Relativistic jets, twin beams of magnetized plasma launch from the immediate vicinity of the black hole at speeds approaching the speed of light, punching outward in opposite directions along the black hole's rotation axis, extending far beyond the host galaxy and into the emptiness of intergalactic space. Not every quasar produces jets. In fact, only about 10 to 15% of quasars are what astronomers call radio loud, meaning they emit powerful radio waves generated by jets. The rest are radio quiet. They have the disk, they have the corona, they have the luminosity, but they lack the dramatic twin outflows that make radio loud quasars among the most visually stunning objects in the cosmos. Understanding why some quasars produce jets and others do not has been one of the central puzzles in active galaxy research for decades, and the answer appears to hinge on one critical property: the spin of the black hole. To understand jets, you first need to understand what a spinning black hole does to the space around it. A non-spinning black hole warps space-time symmetrically. Space curves inward toward the center equally in every direction. There is an event horizon, a point of no return, and inside that horizon, everything falls toward the singularity. Simple, symmetric, and relatively well understood. A spinning black hole is different. When a black hole rotates, it does not just sit passively inside curved spacetime. It actively drags spacetime around with it like a spinning ball embedded in thick honey. The honey near the ball gets pulled along, forced to rotate in the same direction as the ball. Closer to the ball, the dragging is stronger. Farther away, it weakens. This effect is called frame dragging, and it is a direct prediction of Einstein's general theory of relativity applied to rotating masses. Around a spinning black hole, frame dragging creates a special region called the ergosphere. The ergosphere lies outside the event horizon. It is not the point of no return. Objects inside the ergosphere can still escape back to the outside universe. But inside the ergosphere, frame dragging is so intense that nothing can remain stationary. Everything, matter, light, magnetic fields, everything must rotate in the same direction as the black hole. There is no resisting it. Space-time itself is being dragged around, and you are embedded in space-time. You must move. Now imagine magnetic field lines anchored in the inner accretion disk, threading upward through the ergosphere. These field lines are frozen into the conducting plasma of the disk, meaning they move with the disk material. But inside the ergosphere, the spinning black hole grabs hold of these field lines through frame dragging and forces them to rotate even faster than the disk itself rotates. The field lines get wound up, twisted tighter and tighter like a coiled spring. This twisting stores enormous electromagnetic energy in the magnetic field structure above and below the black hole. In 1977, astrophysicists Roger Blanford and Roman Znajek published a landmark paper showing mathematically what happens when magnetic field lines thread through the ergosphere of a rapidly spinning black hole. The frame dragging twists the field lines into a tight helical configuration, like a corkscrew. This helical structure creates an electromagnetic force, a pointing flux, that drives energy and plasma outward along the rotation axis. The energy does not come from the accretion disk. It comes from the rotational energy of the black hole itself. The spinning black hole acts like a massive electromagnetic generator. Its rotation winds up the field lines, the wound field lines launch jets, and the energy carried away by the jets is extracted from the black hole's spin. Over time, the black hole actually slows down as the jets drain its rotational energy. The black hole is paying for the jets with its own angular momentum. This is the Blanford-Znarek mechanism, and it is the leading theoretical explanation for how relativistic jets are powered. The mechanism explains several key observations. First, it explains why jets require a spinning black hole. A non-spinning black hole does not drag spacetime and cannot wind up field lines into the helical configuration needed to launch jets. Second, it explains why jet power correlates with black hole spin. Faster spinning black holes drag spacetime more aggressively, wind field lines more tightly, and produce more powerful jets. Third, it explains why jets emerge along the rotation axis. The helical field structure naturally collimates the outflow into two narrow beams aimed along the spin axis, perpendicular to the accretion disk. The reason only some quasars produce powerful jets now becomes clearer. If a supermassive black hole has accumulated its mass through a long history of chaotic, may randomly oriented accretion events, with gas falling in from different directions at different times, the angular momentum of the infalling material partially cancels out. The black hole ends up spinning relatively slowly. Slow spin means weak frame dragging, which means weak jets or no jets at all. But if the black hole grew primarily through prolonged, steady accretion from a single direction, or through major galaxy mergers that funneled gas consistently along one axis, the angular momentum adds up. The black hole spins rapidly. Rapid spin means powerful frame dragging, which means powerful jets. The 10 to 15% of quasars that are radio loud may simply be the ones whose central black holes happen to be spinning fast enough to drive the Blanford-Znarek mechanism efficiently. There is also the question of magnetic field strength and geometry. Even a rapidly spinning black hole cannot launch jets without sufficiently strong and well-ordered magnetic fields threading the ergosphere. If the magnetic field near the black hole is tangled and chaotic, with no coherent large-scale structure, the Blanford-Znarek mechanism cannot operate efficiently. The field needs a degree of organization, a net vertical component threading through the horizon region, to be wound up effectively. Some accretion flows may achieve this configuration naturally, while others may not. This adds another variable to the jet launching equation and helps explain why the relationship between spin and jet power is not perfectly simple. Before we describe the jets themselves, it helps to understand the physical region where the jet is actually born. The launching zone sits directly above the poles of the black hole, inside a narrow funnel-shaped channel that opens above and below the inner accretion disk. In this funnel, conditions are radically different from the dense, hot disk nearby. The gas density drops sharply. Matter that would normally fill this space gets pushed away by the combination of radiation pressure from the disk below and magnetic pressure from the increasingly organized field lines threading upward through the ergosphere. What remains is a magnetically dominated region, a space where the energy stored in the magnetic field far exceeds the energy in the matter itself. In most of the accretion disk, gas dominates and drags the magnetic field along with it. But in the polar funnel, the relationship is reversed. The magnetic field dominates and it controls the motion of whatever plasma is present. This reversal is critical. When the magnetic field is strong enough to dominate the dynamics, it can accelerate plasma to extraordinary speeds. The helical field structure created by the Blandford-Znajek mechanism acts like a magnetic spring that uncoils along the rotation axis, flinging material outward. At the same time, the magnetic pressure gradient between the tightly coiled inner field and the weaker outer field drives a continuous outflow. The funnel walls, defined by the boundary where disk material meets the magnetically dominated zone, confine this outflow into a narrow channel. The plasma gets squeezed, focused, and accelerated through the funnel like water through a nozzle. By the time it clears the funnel and emerges into open space above the disk, the plasma is already moving at a significant fraction of the speed of light. Further acceleration continues along the jet as the helical field continues to unwind and drive the outflow. Now, let us talk about what the jets actually are, because they are far more complex than most people imagine. When you hear the word jet, you might picture a clean beam of light shooting out from the black hole like a laser pointer. That is not what these objects are. A relativistic jet from a quasar is a structured, magnetized, collimated outflow of plasma, meaning a mix of charged particles threaded by powerful magnetic fields, accelerated to speeds exceeding 99% of the speed of light in some cases. It is not a beam of light. It is a river of matter and energy, confined and guided by its own magnetic field structure, plowing through the surrounding environment at nearly the ultimate speed limit of the universe. And there is an important question about those charged particles that remains unresolved. What exactly are jets made of? Two main possibilities exist, and distinguishing between them has proven remarkably difficult. The first possibility is that jets are composed primarily of electrons and positrons, their antimatter counterparts, created as pairs from pure energy near the black hole. Such a jet would be relatively light, carrying enormous energy but comparatively little mass. The second possibility is that jets contain normal matter, electrons and protons, dragged from the inner disk and accelerated along with the magnetic field. A proton-loaded jet would carry far more mass, since a proton is roughly 1,800 times heavier than an electron, requiring more power to accelerate and hitting the surrounding medium harder when it finally decelerated. The truth is, we do not know for certain which picture is correct. Observations of synchrotron radiation from jets tell us that relativistic electrons are present, but synchrotron emission alone cannot distinguish between electrons paired with positrons and electrons paired with protons. Some jets may be predominantly electron-positron, others predominantly electron-proton, and still others a hybrid of both. The composition may even change along the jet's length, starting as a paired-dominated flow near the black hole and entraining heavier matter from the surrounding environment as it propagates outward. This is an active area of research, and resolving it would fundamentally change our understanding of how much energy jets carry and how they interact with their environment. The magnetic field within the jet has a helical structure, a corkscrew shape inherited from the twisting process that launched it. This helical field acts like a magnetic nozzle, confining the plasma and preventing it from spreading out. Without the magnetic confinement, the jet would expand and dissipate almost immediately after launch. The magnetic field holds it together, keeping the outflow narrow and focused over extraordinary distances. Some jets remain collimated across hundreds of thousands of light years. Think about what that means. A structure launched from a region smaller than the solar system maintains its coherence across distances comparable to the diameter of the entire Milky Way galaxy. As the jet plows outward, it does not flow smoothly. The plasma within the jet moves at different speeds in different regions. Faster moving material catches up to slower moving material ahead of it. And when the two collide, the result is an internal shock. At these shock fronts, particles get accelerated to even higher energies than they had before. The acceleration mechanism is related to what happens when you bounce a ball between two approaching walls. Each bounce speeds the ball up. Similarly, charged particles bouncing back and forth across a shock front gain energy with each crossing. This process can boost particles to extraordinarily high energies, turning them into relativistic missiles carrying the kinetic energy of macroscopic objects despite being subatomic in size. These internal shocks are visible. When astronomers observe jets in radio waves, X-rays, and sometimes even visible light, they see bright knots along the jet's length. These knots are the shock fronts, regions where particle acceleration is most intense and radiation output is highest. The radiation from these knots comes primarily from synchrotron emission, light produced when relativistic electrons spiral around magnetic field lines. As a charged particle spirals in a magnetic field, it constantly changes direction, which counts as acceleration. Any accelerating charged particle emits electromagnetic radiation. When the particle is moving at nearly the speed of light, the emitted radiation is boosted in energy and concentrated into a narrow forward cone. The result is synchrotron radiation, a distinctive type of emission with a characteristic spectrum and polarization that tells astronomers the electrons producing it are relativistic, and that strong magnetic fields are present. Synchrotron radiation from jets spans an enormous range of the electromagnetic spectrum. The most energetic electrons produce X-rays and sometimes even gamma rays. Less energetic electrons produce optical and infrared light. And the bulk of the jet's synchrotron emission typically falls in the radio waveband, which is why jets are most easily detected by radio telescopes. When you see images of quasar jets taken at radio wavelengths, the glowing structures you see are not hot gas in the traditional sense. They are synchrotron-emitting relativistic plasma, matter so energized that it glows through an entirely different physical mechanism than anything in everyday experience. Jets also produce a striking observational illusion that confused astronomers for years. When a jet is aimed roughly toward us, close to our line of sight, the material in the jet appears to be moving faster than the speed of light. This apparent superluminal motion is not a violation of physics. Nothing is actually exceeding the cosmic speed limit. It is a geometric projection effect. When a jet moves at 98 or 99% of light speed at a small angle to our line of sight, the combination of the jet's actual velocity and the finite travel time of light creates an illusion. The jet appears to cover more angular distance on the sky per unit time than light should allow. Imagine a fire truck with its siren on, driving toward you at high speed. The sound waves get compressed, making the siren sound higher pitched than it actually is. Something analogous happens with light from a jet aimed toward us. The motion compresses time intervals and boosts apparent velocities, making the jet appear to move superluminally. Once astronomers understood this effect, apparent superluminal motion became a powerful diagnostic tool. By measuring the apparent speed and the jet's brightness properties, they can calculate the true speed of the jet and its angle to our line of sight. At the far end of the jet, where the outflow finally slams into the surrounding intergalactic medium, enormous structures form. The jet material decelerates abruptly when it hits the denser external gas, creating a termination shock. Behind this shock, the jet plasma accumulates in vast, diffuse, billowing clouds called radiolobes. These lobes can be enormous, extending hundreds of thousands of light years from the host galaxy, far larger than the galaxy itself. A single quasar with powerful jets can inflate radiolobes that dwarf everything else in its cosmic neighborhood. The radiolobes glow with synchrotron radiation from the accumulated relativistic plasma. And at the leading edge, where the jet currently impacts the intergalactic medium, there is often a bright, compact region called a hotspot. The hotspot marks the active working surface of the jet, the point where fresh energy is being dumped into the lobe. The lobes themselves are old, fading repositories of energy deposited over millions of years of jet activity. They are like the exhaust plume of a rocket, except the plume is made of magnetized relativistic plasma, and it fills a volume larger than a galaxy. Some of the best studied jet systems illustrate this structure beautifully. The giant elliptical galaxy at the heart of the Virgo cluster, M87, hosts a famous jet visible even in optical light, a narrow beam extending thousands of light years from the galaxy's nucleus, punctuated by bright knots that mark internal shock fronts. The radio galaxy Cygnus A, one of the most powerful radio sources in the sky, displays twin jets terminating in spectacular radio lobes, separated by roughly 500,000 light years, with bright hotspots at the outer edges where the jets are actively driving into the surrounding gas. These structures are visible evidence of the Blandford-Znajek mechanism in action. Rotational energy extracted from a spinning supermassive black hole and deposited across intergalactic space in the form of magnetized relativistic plasma. The total energy contained in these lobes is staggering. A single pair of radio lobes can contain energy equivalent to millions of times the entire energy output of the Sun over its 10 billion year lifetime. All of that energy was extracted from the accretion process, and the black hole's spin, channeled through the magnetic field structure near the event horizon, launched as a jet, and deposited hundreds of thousands of light years away. The jet is an energy pipeline connecting the smaller scales in the universe, the immediate vicinity of the event horizon, to some of the largest structures known. It transports energy from a region smaller than the solar system to a volume larger than a galaxy. No other physical process bridges such an enormous range of scales, and the jets do more than just carry energy outward. As they plow through the gas surrounding the host galaxy, they heat it, compress it, push it aside, and disrupt it. The jets interact with their environment in powerful ways that have consequences not just for the quasar itself, but for the entire galaxy and even the cluster of galaxies in which it resides. These interactions, this feedback between the quasar's jets and the surrounding gas, play a central role in determining whether the quasar continues to shine or whether it ultimately chokes off its own fuel supply and goes dark. But before we explore how the quasar engine shuts itself down, we need to move outward from the central inferno and examine the structures that surround it. Because just beyond the blazing inner engine, beyond the disk and the corona and the base of the jets, lies a region where fast-moving gas clouds orbit through an intense radiation field, absorbing and re-emitting light in patterns that reveal the hidden conditions deep inside. And beyond that, a thick wall of dust and gas encircles the entire machine. A wall so opaque that it can hide the quasar's true nature from observers who happen to be looking from the wrong direction, Move outward from the accretion disk, past the corona, past the launching point of the jets, and you enter a region that looks nothing like the ordered spiral of the inner engine. Here, at distances of light days to light months from the black hole, space is filled with dense clouds of gas. Not a smooth, continuous flow, but individual clumps, thousands of them, each one roughly the size of our solar system or smaller, racing through the quasar's radiation field at extraordinary speeds. Some of these clouds are hurtling toward us, some are flying away, some are moving sideways across our line of sight. They orbit the black hole in a thick, chaotic swarm, and they are moving fast. Typical speeds range from 1,000 to 10,000 kilometers per second. At the upper end, that is more than 3% of the speed of light. These clouds are not gently drifting. They are screaming through space at velocities that would carry them from Earth to the Moon in under 40 seconds. This region is called the broadline region, and it earns its name from what its light looks like when you spread it into a spectrum. Every element in the periodic table absorbs and emits light at specific wavelengths. These wavelengths are as unique as fingerprints. Hydrogen emits at one set of wavelengths, carbon at another, magnesium at another. When you pass the light from any glowing source through a prism or a spectrograph, you can identify which elements are present by looking for their characteristic wavelengths. Astronomers have been doing this for well over a century, and it remains one of the most powerful tools in astrophysics. When the intense ultraviolet radiation from the accretion disk strikes the gas clouds in the broadline region, it ionizes them. It strips electrons away from atoms, breaking them apart. When those electrons eventually recombine with the ions, or when excited atoms release energy by dropping to lower energy states, the gas emits light at specific characteristic wavelengths. These are emission lines, bright spikes in the spectrum at wavelengths, determined by the atomic physics of whatever element is doing the emitting. In a quasar, the strongest emission lines come from hydrogen, carbon, magnesium, silicon, and oxygen, elements that are common in cosmic gas and that have emission lines well suited to the temperatures and densities present in the broadline region. But here is what makes these emission lines so distinctive. They are broad, not narrow, sharp spikes like you would see from a stationary gas cloud in a laboratory, but wide, smeared out humps spread across a significant range of wavelengths on either side of the expected position. This broadening is caused by the Doppler effect. When a source of light moves toward you, its wavelength gets compressed. The light shifts toward shorter wavelengths, toward the blue end of the spectrum. When a source moves away from you, the wavelength stretches. The light shifts toward longer wavelengths, toward the red end. The faster the source moves, the greater the shift. In the broadline region, thousands of gas clouds orbit the black hole at thousands of kilometers per second. Some are on the near side of their orbits, moving toward us. Their emission is blue shifted. Some are on the far side, moving away from us. Their emission is red shifted. Some are moving sideways, contributing light at the unshifted central wavelength. Add all of these contributions together, from all the clouds at all their different velocities and orbital orientations, and the result is an emission line that is massively broadened. Instead of a sharp spike, you get a wide bump whose total width directly reflects the range of velocities present in the cloud population. The width of these broad emission lines tells astronomers how fast the clouds are moving. And because the clouds are orbiting in the black hole's gravitational field, their speed is directly related to the black hole's mass and their distance from it. Faster motion means either a more massive black hole pulling harder, or clouds orbiting closer to the center, or both. This simple relationship between line width and orbital velocity makes the broadline region one of the most valuable diagnostic tools for studying the hidden interior of a quasar. You cannot see the black hole. You cannot see the inner disk directly in most cases, but you can see the emission lines from these orbiting gas clouds, and those lines carry encoded information about the gravitational environment deep inside. Different emission lines come from different regions within the broadline cloud population and reveal different physical conditions. The hydrogen alpha line, emitted when an electron drops from the third energy level to the second in a hydrogen atom, is one of the strongest and most commonly observed. It tells astronomers about the overall density and extent of the ionized hydrogen gas. The carbon-4 line, emitted by carbon atoms that have been stripped of 3 of their 6 electrons, requires much more energetic ultraviolet radiation to produce. Its presence indicates that the central engine is flooding the broadline region with photons energetic enough to ionize carbon 3 times over. The magnesium-2 line, from magnesium that has lost 1 electron, is particularly useful for studying quasars at moderate cosmological distances, because it falls in a convenient part of the spectrum after being redshifted by the expansion of the universe. Each line provides a different piece of the puzzle. The relative strengths of different lines reveal the temperature, density, chemical composition, and ionization state of the gas. Together, they paint a surprisingly detailed portrait of conditions inside the quasar, all extracted from light that has traveled billions of years across the universe. There is another extraordinary technique that uses the broadline region to directly measure something that would otherwise be impossible to determine: the mass of the central black hole. The method is called reverberation mapping, and it works like an echo. Accretion disks do not shine at perfectly constant brightness. Their luminosity fluctuates. Sometimes more gas piles up in the inner disk, friction intensifies, and the disk brightens. Sometimes the flow slows and the disk dims. These fluctuations can happen over days or weeks, and astronomers can track them by monitoring a quasar's brightness over time. Now, the broadline region gas is ionized by the radiation from the disk. When the disk brightens, the increased flood of ultraviolet photons ionizes more gas in the broadline clouds, causing the emission lines to brighten in response. When the disk dims, the emission lines fade. The broadline region echoes the disk's behavior, but the echo is delayed. The broadline clouds are not right next to the disk. They are light days or light weeks away. The increased radiation from the disk has to travel outward at the speed of light before it reaches the clouds and triggers the stronger emission. This light travel time creates a measurable lag between the disk's brightness change and the broadline region's response. By carefully monitoring both the disk's continuum brightness and the strength of specific emission lines over weeks and months, astronomers can measure this time delay precisely, and the time delay gives them a distance. If the broadline region responds 12 days after the disk flares, then the clouds must be roughly 12 light days from the central engine. That is a direct physical measurement of the size of the broadline region, obtained purely from timing. Once you know the distance from the black hole to the broadline clouds, and you know how fast those clouds are moving from the width of the emission lines, you have everything you need to calculate the black hole's mass. The relationship is straightforward. Gravity sets the orbital speed at any given distance. A more massive black hole requires faster orbits at the same distance. A less massive one allows slower orbits. By combining the measured distance from reverberation mapping with the measured velocity from the line width, astronomers can calculate the mass of the black hole using the same basic gravitational physics that lets us weigh our own sun by measuring Earth's orbital speed and distance. This technique has been applied to hundreds of quasars and active galactic nuclei over the past few decades. It has revealed supermassive black holes with masses ranging from about 1 million to several billion times the mass of our sun. And all of this information, the mass of an invisible object billions of light years away, was extracted from the flickering of emission lines produced by gas clouds smaller than our solar system. It is one of the most elegant measurement techniques in all of observational astronomy. Now let us move further outward still, to a structure that changes everything about how we see the quasar. Beyond the broad line region, at distances of roughly a few light months to several light years from the black hole, lies a vast thick structure of gas and dust. It wraps around the central engine in a roughly donut-shaped configuration, encircling the disk, the corona, the jet bases, and the broad line region like a fat ring surrounding a brilliant jewel. This structure is called the dusty torus. The dusty torus is made of the same kinds of material you find throughout the interstellar medium of any galaxy. Microscopic grains of silicate minerals and carbon compounds, mixed with denser clumps of molecular gas. These are the same kinds of dust that fill the spaces between stars in our own Milky Way. The same kinds of grains that block our view of the galactic center, the same kinds of particles that scatter starlight and make reflection nebulae glow. There is nothing exotic about the material itself. What makes the torus remarkable is where it is and what it does. The inner edge of the torus marks a critical boundary. Closer to the central engine, the radiation field from the accretion disk is so intense that dust grains cannot survive. The flood of ultraviolet and X-ray photons carries so much energy that it heats any dust grain to the point where the grain sublimates, transitioning directly from solid to gas. For typical silicate dust grains, this happens at a temperature of roughly 1,500 degrees. The distance from the central engine where the radiation field heats dust to exactly this temperature is called the sublimation radius. Inside the sublimation radius, no dust exists. The radiation has vaporized it all. Gas can survive there because gas does not sublimate, it simply gets hotter. But solid grains are destroyed. The sublimation radius defines the inner wall of the torus. Outside the sublimation radius, dust grains survive. They absorb the ultraviolet and optical radiation pouring outward from the central engine, and they re-emit that absorbed energy as infrared light. Warm dust glows in the infrared, and quasars are indeed powerful infrared sources. A significant fraction of a quasar's total energy output appears in the infrared, and much of that infrared emission comes from dust in the torus that has absorbed higher energy radiation from the disk and re-radiated it at longer wavelengths. The torus acts as a reprocessing layer, intercepting some of the disk's output and converting it from ultraviolet to infrared. But the most important role of the dusty torus is not what it emits, it is what it blocks. The torus is thick, not thin and wispy like a ring of smoke, but geometrically fat, extending well above and below the plane of the accretion disk. If you imagine the accretion disk as a flat plate lying horizontally, the torus rises up on all sides like the walls of a deep bowl. From certain angles, Looking down into the bowl from above or at a moderate angle, you can see straight through to the brilliant disk, the hot corona, and the fast-moving clouds of the broad line region. Everything is visible. The full glory of the Quasar engine is on display. But from other angles, looking at the system nearly edge-on, the thick wall of the torus blocks your view entirely. The disk is hidden behind a wall of opaque dust. The corona is obscured. The broad line region sitting inside the torus is invisible. All you can see is the outer surface of the torus glowing in the infrared, and whatever structures exist beyond the torus at larger distances. This realization led to one of the most important unifying ideas in the study of active galaxies. For decades, astronomers had been classifying active galaxies into bewilderingly different categories based on how they appeared in telescopes. Some showed brilliant point-like nuclei with broad emission lines, indicating fast-moving gas close to a central engine. Others showed much fainter nuclei with only narrow emission lines, suggesting slower-moving gas at greater distances. Some were powerful radio sources with dramatic jets. Others had no detectable radio emission at all. The taxonomy grew increasingly complicated, with names like Seyfert 1, Seyfert 2, Broadline Radio Galaxy, Narrowline Radio Galaxy, Blazar, and Quasar being applied to what seemed like fundamentally different types of objects. But a striking pattern emerged. The objects with broad emission lines and brilliant nuclei, the Type 1 sources, also tended to show strong X-ray emission, powerful ultraviolet flux, and rapid variability. All the signatures you would expect if you were looking directly at the inner accretion engine. The objects with only narrow emission lines and fainter nuclei, the Type 2 sources, were missing exactly the features that required a direct view of the central engine. They had the narrow lines from more distant gas, the infrared emission from warm dust, sometimes even radio jets, but the broad lines, the X-rays, the rapid variability from the inner disk, all absent. The unification model proposed a deceptively simple explanation. These are not different machines, they are the same machine seen from different directions. A Type 1 quasar is a quasar viewed from above, or at a moderate angle to the torus. The observer's line of sight passes over the torus wall, or through a gap in its structure, and reaches the central engine directly. The brilliant disk is visible. The corona is visible. The broadline region is visible. The full spectrum of the quasar, from radio through infrared, through optical, through ultraviolet, through X-ray, is on display. Broad emission lines dominate the spectrum because the fast-moving clouds close to the black hole are directly observable. A Type 2 quasar is the same quasar viewed from the side, at an angle where the thick, dusty torus blocks the direct line of sight to the center. The accretion disk is hidden. The corona is hidden. The broadline region is hidden. The observer cannot see any of the structures inside the torus. What the observer can see are structures that exist outside the torus, at larger distances from the central engine. And one such structure is the narrow line region. The narrow line region sits much further from the black hole than the broadline region. It extends from tens of light years to thousands of light years from the center, well beyond the outer edge of the torus. The gas clouds here are illuminated by the same central radiation source, ionized by the same ultraviolet photons that ionize the broadline clouds. But they are much farther away, in a weaker gravitational field, and so they orbit much more slowly. Typical velocities in the narrow line region are only a few hundred kilometers per second. compared to thousands in the broadline region. Because the clouds move more slowly, the Doppler broadening of their emission lines is much less extreme. The resulting emission lines are narrow, sharp, and well-defined. These narrow lines are visible from any viewing angle because the narrow line region is far enough from the center that the torus does not block it. The narrow line region is above, below, and around the torus, fully exposed to any observer regardless of orientation. So a Type 2 quasar shows narrow emission lines from the distant narrow line region, infrared emission from the warm torus, and sometimes radio emission from jets that extend far beyond the torus in both directions. But it lacks the broad emission lines, the strong X-ray flux, and the rapid optical variability that characterize a Type 1 source. Not because those features are absent, but because they are hidden behind a wall of dust. The central engine is running at full power, the disk is blazing, the corona is producing X-rays, the broadline clouds are racing around at thousands of kilometers per second. But none of that light reaches the observer because the torus intercepts and absorbs it. The most compelling evidence for the unification model came from a clever observational technique called spectropolarimetry. Light can be polarized, meaning its electromagnetic waves oscillate preferentially in one direction rather than randomly. When light scatters off dust grains or free electrons, it tends to become polarized. Astronomers realized that even in a Type 2 source, where the direct view of the central engine is blocked, some light from the hidden broadline region might escape by scattering off material located above or below the torus. This scattered light would take an indirect path, bouncing off electrons or dust in regions that have a clear view of both the central engine and the observer. Because it's scattered, this light would be polarized. When astronomers pointed spectropolarimeters at certain Type 2 active galaxies and filtered for polarized light only, they found exactly what the unification model predicted. Hidden broad emission lines appeared in the polarized spectrum. The broad lines were there all along, produced by fast-moving gas clouds near the black hole. But their light was being blocked along the direct line of sight by the torus. Only the small fraction of broadline light that happened to scatter off material above the torus, picking up polarization in the process, could reach the observer. This was powerful, nearly conclusive evidence that Type 1 and Type 2 active galaxies contain the same central engine, and that the differences between them are caused by viewing geometry, not by fundamental physical differences. The unification model does not explain everything perfectly. Reality is more complicated than a simple, clean donut of dust surrounding a neat disk. The torus is probably not a smooth, uniform structure. Modern observations and simulations suggest it is clumpy, composed of individual dense clouds rather than a continuous wall. The clumpy structure means that the boundary between Type 1 and Type 2 is not perfectly sharp. Some lines of sight might pass between clumps and catch a partial glimpse of the central engine. Others might graze a clump and see a partially obscured view. The transition between Type 1 and Type 2 is probably gradual, with a range of intermediate cases where partial obscuration produces mixed spectral signatures. The geometry of the torus may also depend on the luminosity of the central engine. More luminous quasars produce more intense radiation, which pushes the sublimation radius outward and may blow dust away from the polar regions, effectively thinning the torus. This is called the receding torus model. At the highest luminosities, the torus might become so thin that nearly every line of sight provides a direct view of the central engine, which would explain why the most luminous quasars are predominantly type 1. Less luminous active nuclei, where the radiation pressure is lower and the torus remains thick, show a higher fraction of type 2 sources. Wind from the disk may also play a role in shaping the torus. Some theoretical models propose that the torus is not a static structure at all, but rather the base of a dusty wind launched from the outer accretion disk. In these models, radiation pressure from the disk drives gas and dust upward and outward, creating a flowing, dynamic structure rather than a stationary ring. The torus would then be constantly replenished by the wind, with new dust being lifted from the disk and old dust being pushed outward or destroyed. This would explain why the torus exists at all, since a static ring of dust would eventually be destroyed by the radiation field or fall inward under gravity. A wind-driven torus is self-sustaining, maintained by the same accretion process that powers the rest of the quasar. These details matter because they affect how we interpret observations of active galaxies across cosmic history. Quasars are most common in the distant universe, at redshifts corresponding to billions of years in the past, when galaxy mergers were frequent and gas supplies were plentiful. When we survey these distant quasars, we need to know how many are hidden behind dusty tori and therefore missing from our catalogues. If the torus geometry depends on luminosity, then our surveys might be biased. We could be missing a large population of obscured quasars, type 2 sources that are just as powerful as the ones we can see, but whose light is blocked by dust along our particular line of sight. Infrared surveys have begun to uncover this hidden population. Because dust absorbs ultraviolet and optical light, but re-emits it in the infrared, obscured quasars that are invisible in optical telescopes can be detected in the infrared. Observations from space-based infrared telescopes have revealed substantial numbers of previously unknown active galaxies, confirming that a significant fraction of the quasar population is obscured at any given time. Some estimates suggest that for every unobscured Type 1 quasar we see, there are 1 to 3 obscured Type 2 quasars hiding behind their dusty tori, equally luminous, equally massive, equally active, but invisible in visible light. This means the total energy output of quasars across cosmic history, their cumulative impact on the universe, is significantly larger than what optical surveys alone would suggest. The quasars we see in visible light are only a fraction of the total population. The rest are there, shining just as fiercely, but their light is being intercepted and reprocessed by dust before it reaches our telescopes. The torus is not just an interesting structural feature. It is a cosmic veil that has hidden a large fraction of the universe's most powerful energy sources from our view for decades. So as you move outward through a quasar, from the event horizon to the inner disk, to the corona and jet base, to the broadline region, and finally to the dusty torus, you encounter a nested set of structures, each one larger than the last, each one shaped by the central accretion process. The disk converts gravitational energy into light. The corona reprocesses that light into X-rays. The jets transport energy across intergalactic distances. The broadline clouds serve as orbital tracers that reveal the black hole's mass. And the torus wraps the whole machine in a directional filter, determining what each distant observer is allowed to see. Every one of these structures exists because matter is falling toward a supermassive black hole. Remove the accretion flow and the disk vanishes. The corona dissipates, The jets starve and fade. The broad-line clouds disperse. The torus, no longer heated and sustained by the central engine, cools and fades into the background of the host galaxy. The entire quasar, every component, every structure, every photon, is a product of accretion. Turn off the fuel supply, and the engine dies. And that is exactly what happens. Quasars do not shine forever. Something stops them. Something shuts down the flow of gas into the central engine, and the most luminous objects in the universe go dark. Understanding what kills a quasar is the final piece of the machine. A quasar is not permanent. Despite its staggering power, despite the fact that it outshines 1 trillion stars and dominates its corner of the visible universe, a quasar carries within itself the seeds of its own destruction. The very processes that make it the brightest sustained object in existence also work to shut it down. The engine does not simply run until the fuel tank empties, it actively destroys its own fuel supply, blowing gas out of the nucleus, heating the surrounding environment until fresh material can no longer fall inward, and gradually starving itself into silence. This self-regulation is one of the most important ideas in modern astrophysics, and it connects the fate of a single black hole to the evolution of an entire galaxy. The most direct way a quasar undermines itself is through radiation pressure. The accretion disk produces an extraordinary flood of photons, and photons carry momentum. When a photon strikes an atom or an electron in the surrounding gas, it delivers a tiny push. One photon delivers an insignificant push, but the quasar produces so many photons, a torrent so dense and energetic that the combined pushing force becomes enormous. Gas near the central engine gets hammered by this relentless outward pressure, and if the pressure is strong enough, it can overcome the inward pull of gravity entirely. There is a critical threshold called the Eddington limit, named after astrophysicist Arthur Eddington, who first calculated it in the early 20th century. The Eddington limit defines the maximum luminosity at which radiation pressure outward exactly balances gravitational pull inward for gas surrounding a massive object. Below this limit, gravity wins. Gas can continue falling inward, feeding the accretion disk, sustaining the quasar's output. At or above this limit, radiation pressure wins. Photons push the gas outward faster than gravity can pull it inward. The infalling fuel gets blown away from the engine. The harder the quasar shines, the harder it pushes against its own food supply. To understand this intuitively, imagine trying to pour water into a fountain that is blasting straight up. At low pressure, water flows down toward the drain. You are feeding the system. But increase the pressure and the spray knocks aside everything you pour in. The water gets blasted back faster than you can deliver it. This is essentially what happens at the Eddington limit. Below it, gravity draws gas inward successfully. Above it, radiation pressure overwhelms gravity. The quasar is trying to feed, but its own luminosity keeps slapping the food away. The Eddington limit depends on the black hole's mass. A more massive black hole has a stronger gravitational pull, which means it can hold onto gas against a more intense radiation field. So more massive black holes can sustain higher luminosities before reaching their Eddington limits. This creates a natural ceiling on how fast a black hole can grow. A black hole accreting at the Eddington limit adds mass at a specific rate determined by its current mass. It grows exponentially, but the time scale for significant growth is tens of millions of years. This Eddington timescale is one of the reasons supermassive black holes cannot have formed instantaneously. They needed hundreds of millions of years of near-continuous feeding to reach the billions of solar masses we observe in the most luminous quasars. And during that entire growth period, the Eddington limit acted as a speed brake, preventing the black hole from consuming gas faster than its own radiation would allow. Many quasars shine at or near their Eddington limit. Some may even exceed it briefly, through special geometric configurations where the radiation escapes preferentially in certain directions, while accretion continues from others. But sustained super Eddington luminosity is difficult to maintain. The radiation pressure launches powerful winds from the surface of the accretion disk, driving gas outward at speeds of thousands to tens of thousands of kilometers per second. These winds are not gentle breezes. They are massive outflows, carrying significant amounts of material away from the central engine, material that would otherwise have spiraled inward and fed the black hole. These radiation-driven winds have been directly observed. When astronomers examine the spectra of luminous quasars, they frequently find absorption features that are blue-shifted, meaning the absorbing gas is moving toward us at high speed. This gas is being blown outward from the quasar's central region along our line of sight. The velocities are enormous, often 5,000 to 50,000 kilometers per second. In the most extreme cases, called ultra-fast outflows, the wind speeds reach a significant fraction of the speed of light. These outflows carry enormous kinetic energy, enough to profoundly affect the gas in the host galaxy far beyond the immediate vicinity of the black hole. When a quasar wind slams into the interstellar medium of its host galaxy, it creates a shock wave that sweeps outward. The shock heats the surrounding gas to millions of degrees, making it too hot to collapse under gravity and form new stars. It also physically pushes gas outward, driving it to larger radii or even expelling it from the galaxy entirely. This process is called radiative feedback, and its effects are dramatic. A quasar powerful enough to drive strong winds can suppress star formation across its entire host galaxy, altering the galaxy's evolution for hundreds of millions of years after the quasar itself has faded. But radiation-driven winds are only one channel of feedback. The other, potentially even more powerful, comes from the relativistic jets we explored earlier. Jets carry energy extracted from the black hole's spin and deposit it at enormous distances from the nucleus. When a jet plows into the gas filling a galaxy cluster, it inflates vast cavities, bubbles of hot, low-density plasma that displace the denser, cooler gas that would otherwise sink toward the cluster center, cool, and potentially fuel further accretion. The Perseus cluster, one of the best-studied galaxy clusters in the sky, provides a vivid example. At the center of this cluster sits a massive galaxy known as NGC 1275. And at the center of that galaxy sits an active, supermassive black hole launching twin jets. Those jets have carved enormous cavities in the hot gas that fills the cluster. Bubbles, tens of thousands of light years across, clearly visible in X-ray images as dark voids where the jet plasma has pushed the surrounding medium aside. The energy required to inflate these cavities is staggering, equivalent to roughly 10 billion joules deposited into the surrounding gas over millions of years. That energy came from the jets, which extracted it from the black hole's spin and the accretion flow, and dumped it into the cluster environment. The heating from these jet-inflated cavities prevents the surrounding gas from cooling. Without jets, the hot gas in a galaxy cluster would gradually radiate away its energy, cool, and flow inward toward the central galaxy. This cooling flow would provide fresh fuel for the black hole, potentially reigniting or sustaining the quasar. But the jets interrupt this cycle. They heat the gas faster than it can cool, preventing it from collapsing inward, cutting off the fuel supply. The jets are performing mechanical feedback, using the kinetic energy of the outflow to regulate the amount of gas available for accretion. It is a thermostat. When too much gas cools and flows inward, accretion increases, the quasar breatons, jets strengthen, and the increased heating pushes gas away and stops the cooling flow. When the gas is successfully heated and dispersed, less material falls inward, accretion decreases, jets weaken, and eventually the gas can begin cooling again, restarting the cycle. This self-regulating loop operates over millions of years, cycling between periods of stronger and weaker activity, maintaining a rough equilibrium between heating and cooling in the cluster core. The combined effect of radiative and mechanical feedback extends far beyond the immediate surroundings of the black hole. It shapes the entire galaxy. And one of the most striking pieces of evidence for this comes from a relationship that astronomers did not expect to find. It is called the M-sigma relation. The M-sigma relation connects two things that seem like they should have nothing to do with each other. On one side is the mass of the supermassive black hole at the center of a galaxy. On the other side is the velocity dispersion of stars in the galaxy's central bulge, meaning how fast the stars are moving in random directions within the bulge. The velocity dispersion is a measure of how massive and how gravitationally bound the bulge is. Bigger, more massive bulges have higher velocity dispersions because the stars need to move faster to remain in orbit within the stronger gravitational field. What astronomers found, starting in the late 1990s, is that these two quantities are tightly correlated. Galaxies with bigger central bulges, as measured by velocity dispersion, have more massive black holes. Galaxies with smaller bulges have less massive black holes. The relationship is not approximate, it is remarkably tight. If you tell an astronomer the velocity dispersion of a galaxy's bulge, they can predict the black hole's mass to within a factor of 2 or so. This is extraordinary because the black hole is tiny compared to the bulge. The black hole's gravitational influence extends only over the innermost few hundred light years. The bulge spans thousands of light years. The two structures differ in size by a factor of roughly 100. There is no reason based on gravity alone for the black hole to know about the bulge, or for the bulge to know about the black hole. They occupy completely different scales. The M-sigma relation implies that the black hole and the galaxy's stellar bulge somehow regulate each other's growth. They co-evolve. As the galaxy grows, the black hole grows. As the black hole grows, it affects the galaxy. The mechanism that connects them across this vast difference in scale is feedback. When the black hole accretes rapidly and shines as a quasar, the resulting winds and jets heat and expel gas from the galaxy's central region. This reduces the fuel available for both further black hole growth and new star formation in the bulge. Both the black hole and the bulge stop growing. If later events, such as a galaxy merger, bring fresh gas into the nucleus, both can resume growing until feedback kicks in again. Over billions of years, repeated cycles of accretion, feedback, quiescence, and renewed accretion lock the black hole mass and bulge mass into the tight relationship we observe today. This means that quasar feedback is not just a local phenomenon affecting gas near the black hole. It is a galactic-scale regulatory mechanism that has shaped the structure of every massive galaxy in the observable universe. Without feedback, simulations show that galaxies would form far too many stars. The most massive galaxies would be much brighter and more star-rich than we actually observe. Gas would cool and collapse freely, forming stars at prodigious rates. But feedback from active black holes prevents this runaway cooling and star formation. It is the thermostat that keeps galaxies in check, and it operates through the accretion engine at the galaxy's heart. Eventually, regardless of feedback cycles, the fuel runs out. The gas reservoir in the galaxy's nucleus is finite. Every kilogram of gas that gets accreted onto the black hole is a kilogram that is gone forever. Every kilogram blown out by winds or heated by jets is a kilogram that may never return, or at least not for hundreds of millions of years. Over time, the combination of consumption and expulsion depletes the available supply. The accretion rate drops, the disk thins, the luminosity fades. But this fading is not instantaneous. A quasar does not switch off like a light bulb. It dims slowly, over millions of years, and if you could watch the process unfold on a compressed timescale, you would see the machine disassemble itself from the inside out. The first change an observer would notice is the broad emission lines weakening. As the disk's luminosity declines, fewer ultraviolet photons reach the broad line region clouds. The clouds are still there, still orbiting, but they receive less ionizing radiation. Fewer atoms get ionized. Fewer electrons recombine and emit light. The broad emission lines that once blazed in the spectrum gradually fade, their peaks shrinking, their profiles narrowing as only the fastest, closest clouds still receive enough radiation to glow. Within a few 100,000 years of the accretion rate dropping significantly, the broad line region has gone quiet. The spectral fingerprints of the inner engine have disappeared. The accretion disk itself dims next. With less gas feeding the outer edge, the disk drains inward without being replenished. It thins, becomes patchy, develops gaps. The innermost regions may continue to glow as the last remaining gas spirals through, but the outer disk has already emptied. The big blue bump in the spectrum fades. The quasar's signature color shifts from brilliant blue-white towards something dimmer and redder as the hottest inner regions lose their fuel. The corona, starved of the magnetic turbulence that sustained it, dissipates. Without vigorous accretion churning the inner disk, the magnetorotational instability weakens. Magnetic field lines are no longer being amplified and twisted at the rates needed to power continuous reconnection. The X-ray output drops. The iron K-alpha reflection features vanish from the spectrum. The corona was never a permanent structure. It was always a creature of the turbulent disk, and when the disk calms, the corona evaporates. The jets, if present, flicker and die. The Blanford-Znajek mechanism requires both the spinning black hole and ordered magnetic fields threading the event horizon. The black hole still spins, but without vigorous accretion to maintain the large-scale field structure. The magnetic configuration needed for jet launching degrades. The jets weaken, sputter, and eventually shut off. But the radio lobes they inflated do not vanish when the jets die. The lobes are vast reservoirs of relativistic plasma deposited over millions of years. Without fresh energy from the jets, the lobes begin to fade, their synchrotron emission dimming as the relativistic electrons radiate away their energy and cool. But this fading takes a very long time. Radio lobes can persist for tens of millions of years after the jets that created them have gone silent. They are ghost structures, echoes of a dead engine, slowly dissolving into the intergalactic medium. Astronomers sometimes find these orphan lobes in radio surveys, vast diffuse structures with no visible active nucleus at their center, relics of quasars that shut down millions of years ago. The dusty torus is among the last components to disappear. Without the intense radiation from the central engine, the dust at the sublimation radius is no longer being vaporized. But the torus was always heated by the disk's radiation, re-emitting absorbed energy as infrared light. As the disk fades, the torus receives less energy, cools, and its infrared glow dims. Over hundreds of thousands of years, the torus becomes just another collection of gas and dust in the galaxy's nucleus, indistinguishable from the ordinary interstellar medium. The cosmic veil that once determined whether observers saw a Type 1 or Type 2 quasar has dissolved. There is nothing left to hide and nothing left to reveal. What remains is a supermassive black hole sitting quietly at the center of its host galaxy. It has not disappeared. It has not shrunk. Every solar mass of gas it consumed during its active phase has been added to its mass permanently. The black hole is now more massive than when the quasar phase began, sometimes significantly more massive. But without fresh gas to feed the accretion disk, it sits in darkness. No disk, no corona, no jets, no broadline region, no dusty torus glowing in the infrared. Just a massive, invisible gravitational presence warping space-time around herself, influencing the orbits of nearby stars, but producing no light of its own. This is the state of nearly every supermassive black hole in the modern universe. The era of peak quasar activity occurred roughly 10 to 12 billion years ago, when the universe was only a few billion years old. At that time, galaxy mergers were common. Gas was plentiful. Supermassive black holes were feeding voraciously, and the cosmos blazed with quasar light. But as the universe aged, merger rates declined. Gas was consumed or expelled. The fuel supply dwindled across the entire galaxy population. One by one, quasars shut down. Their central black holes went dormant. Today, the vast majority of supermassive black holes are quiet. They are relics of a more violent past. Sleeping engines that once powered the brightest objects in creation. Our own galaxy, the Milky Way, hosts a supermassive black hole at its center. It is called Sagittarius A star, and it has a mass of roughly 4 million times the mass of our Sun. By quasar standards, that is modest. The supermassive black holes powering the most luminous quasars can reach masses of 1 billion or even tens of billions of solar masses. TON 618, one of the most massive known black holes, has an estimated mass of roughly 66 billion times our Sun. Sagittarius A star is a relative lightweight, and right now, Sagittarius A star is nearly silent. It accretes only a tiny trickle of gas, captured from the stellar winds of nearby stars. Its current luminosity is roughly 1 billion times less than its Eddington limit. It is the faintest supermassive black hole we can study in detail, precisely because it is so close to us, only about 26,000 light-years away at the center of our own galaxy. If you could somehow see through the dust that blocks the galactic center in visible light, Sagittarius A star would still be invisible. It produces almost no radiation. It is the very definition of a dormant engine. But it was not always this way. There is compelling evidence that Sagittarius A star was far more active in the relatively recent past. In 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered two enormous structures extending above and below the galactic plane. These structures, now known as the Fermi bubbles, are roughly 25,000 light-years tall each, spanning a total of 50,000 light-years from top to bottom. They are filled with high-energy particles and emit gamma rays and X-rays. The amount of energy required to inflate these bubbles is enormous, and the most likely explanation is that Sagittarius A star experienced a period of significantly enhanced activity a few million years ago. Not full quasar-level luminosity, but a dramatic increase over its current near silence. Perhaps a large cloud of gas fell toward the center and temporarily reignited the accretion engine. Perhaps a star wandered too close and was torn apart by tidal forces, providing a brief but intense burst of fuel. Whatever the cause, the Fermi bubbles stand as evidence that even a dormant black hole can wake up. There's even more direct evidence from an even more recent outburst. Giant molecular clouds near the galactic center, in a region known as Sagittarius B2 and surrounding complexes, have been observed glowing in X-rays in a way that cannot be explained by any local energy source. These clouds are cold and dense. They should be dark in X-rays, but they are not. They are fluorescing, re-emitting X-ray radiation that struck them from an external source. The X-ray pattern is consistent with a powerful flash of radiation that originated from the direction of Sagittarius A star and struck these clouds like a spotlight. By measuring how the X-ray glow shifts from cloud to cloud over the years, astronomers have reconstructed the geometry. The flash came from the galactic center, and based on the light travel time between Sagittarius A star and the clouds, the outburst happened only a few hundred years ago. Just a few centuries back, our galaxy's central black hole flared dramatically, briefly producing X-ray luminosity roughly 1,000,000 times greater than its current output. The flare has long since ended, but the X-ray echo is still bouncing off molecular clouds in the galactic center, like the light from a camera flash still illuminating the walls of a room after the flash itself has faded. We are watching the ghost of an outburst that happened before the telescope was even invented, preserved in the reflected X-ray glow of distant gas clouds. Sagittarius A star is dormant now, but it was not dormant 300 years ago. The engine flickered, however briefly, within recent human history, and on much larger timescales, dormant black holes can return to full quasar luminosity. The trigger is almost always a galaxy merger. When two large galaxies collide, the gravitational disruption funnels enormous quantities of gas toward the center of the resulting merged system. Gas that had been orbiting peacefully in the disks of both galaxies gets stripped from its stable orbits, loses angular momentum through collisions and gravitational torques, and streams inward toward the central supermassive black hole. If enough gas reaches the nucleus quickly enough, the accretion rate surges. A new disk forms, the corona reappears, jets may reignite, the broadline region lights up, the dusty torus reestablishes itself, a quasar is reborn. We can see this process happening in the universe today. Ultra-luminous infrared galaxies, systems where two galaxies are in the process of merging, often show signs of buried quasar activity at their centers, hidden behind thick shrouds of gas and dust, stirred up by the collision. ARP 220, one of the nearest ultra-luminous infrared galaxies, is a violent merger in progress with two nuclei separated by only about 1,000 light-years. Both nuclei show evidence of active black holes feeding on the gas churned up by the collision. Markarian 231, another nearby system, hosts a quasar that appears to have been triggered by a recent merger event. These objects are laboratories for studying the reignition process in real time, watching dormant engines roar back to life as fresh fuel floods the nucleus. Our own Milky Way faces this prospect in the distant future. In roughly 4.5 billion years, the Milky Way will collide and merge with the Andromeda Galaxy. Andromeda also hosts a supermassive black hole at its center, with a mass of roughly 100 million solar masses, about 25 times more massive than Sagittarius A star. When the two galaxies merge, their central black holes will eventually spiral toward each other and combine into a single, more massive black hole. The merger process will funnel gas inward, and there is a real possibility that the resulting black hole will experience a period of enhanced accretion. Perhaps not a full-blown luminous quasar, since both galaxies may have relatively little gas remaining by that time, but at least a significant increase in activity compared to the current near dormancy of both black holes. If that happens, the merged galaxy, the successor to our Milky Way, will briefly host an active nucleus at its center. The descendants of our Sun, if any exist by then, would look toward the galactic center and see something that had not been seen there in billions of years. An accretion engine, shining with energy drawn from matter, spiraling into a supermassive black hole. A small echo of the quasar era, playing out one last time in a universe that has grown far quieter and emptier than it was when quasars ruled the sky. This is the full picture of what happens inside a quasar. It is not a single object. It is a machine with many interconnected components, each one driven by the same fundamental process: accretion. The conversion of gravitational potential energy into radiation and kinetic outflow as matter spirals into a supermassive black hole. The accretion disk is where gravity does its work, where friction from the magnetorotational instability converts orbital energy into heat and light, producing the multi-temperature thermal glow that makes the quasar visible across billions of light years. The corona is where magnetic reconnection superheats plasma above the disk, producing X-rays through inverse Compton scattering. The jets are where ordered magnetic fields, threading a spinning black hole, extract rotational energy through the Blandford-Znajek mechanism, launching structured magnetized plasma outflows at nearly the speed of light across intergalactic distances. The broad line region is where fast-moving gas clouds orbit the black hole, their Doppler-broadened emission lines encoding the mass and conditions of the central engine. The dusty torus is where geometry determines destiny, wrapping the machine in a directional filter that makes the same quasar look fundamentally different depending on the observer's viewing angle. And feedback, both radiative and mechanical, is where the engine's own output regulates its fuel supply, shaping the evolution of the host galaxy and ultimately shutting the quasar down. Every one of these components is a different expression of what accretion does under extreme conditions. The disk is accretion converting gravity into light. The corona is accretion powering magnetic energy release. The jets are accretion and spin powering relativistic outflows. The broadline region is accretion creating an intense radiation field that ionizes surrounding gas. The torus is accretion's radiation field defining the boundary where dust can survive. Feedback is accretion's output acting back on accretion's input. It is all one process, viewed from different angles at different distances, producing different manifestations of the same underlying physics. And when the accretion stops, everything stops. The disk fades, the corona dissipates, the jets die, the emission lines vanish, the torus cools and dissolves into the background, the quasar goes dark. What remains is a supermassive black hole, massive and permanent but utterly silent, sitting at the center of its galaxy like a retired engine in a museum. All the evidence of its active past, the radio lobes inflated by its jets, the heated gas in its galaxy cluster, the chemical elements forged in the stars that its feedback helped regulate, all of that endures. But the engine itself is quiet, and that phrase, the chemical elements forged in stars that its feedback helped regulate, deserves one final moment of attention, because it connects the quasar to you. Quasar feedback did not just shape galaxies in the abstract, it shaped the specific galaxy you live in, the heavy elements in your body, the iron in your blood, the calcium in your bones, the oxygen you're breathing right now were forged in the cores of massive stars and scattered across space when those stars exploded. But which stars formed, and where, and when, was partly determined by quasar feedback operating billions of years before our solar system existed. The supermassive black hole at the center of some ancestral galaxy that eventually became the Milky Way went through its quasar phase long ago. Its winds and jets regulated the galaxy's evolution, helping set the conditions under which our sun and its planets formed. The iron in your blood was forged in a star, whose existence was permitted by a quasar that went dark before our sun was born. You are, in a sense, a downstream consequence of accretion. The same gravitational process that lit up quasars across the early universe also. Through a chain of cause and effect, stretching across billions of years, helped create the conditions for your existence on this small planet orbiting an ordinary star. The quasar engine and your own body are connected by the same thread of physics that runs through this entire story. Matter falls inward, energy flows outward, galaxies are shaped, stars form, planets condense, and eventually, on at least one of those planets, matter arranges itself into a pattern complex, enough to look back at the quasar and understand what it is seeing. The next time you look at a picture of a quasar, a brilliant point of light shining from the edge of the observable universe, remember what you are actually seeing. You are not seeing a black hole. You are seeing what happens when matter falls toward a black hole and fights every step of the way. You are seeing friction and turbulence and magnetic violence, converting the energy of a gravitational fall into the most luminous sustained light the universe has ever known. You are seeing an engine that can outshine 1 trillion suns, reshape a galaxy, and then go dark when the fuel runs dry. You are seeing accretion. The simplest idea in physics, things fall down, taken to its most extreme and spectacular conclusion.